G'day everyone. Day 6, feedback microammeter. There's basically 3 different ways you can measure current. The most common, which a multimeter might use, is to insert a resistance in series with the current and then measure the voltage dropped across that resistance. Such a resistor is called a shunt. So generally that's known as the shunt method. You can also use the magnetic field that a current produces. That's used in clamp-on meters. For DC clamp-on meters, which do exist, they generally have a Hall sensor, and they need some mechanism of zeroing because they're not induction based. Whereas an AC one would be based on a little transformer, essentially, a current transformer. But in DC, for measuring very small currents, the magnetic field produced is actually quite tiny, so that's not terribly practical for microamps and below. This is like another method, which is called a feedback ammeter. So what it does is it's basically a transimpedance amplifier, and it sinks or sources current to essentially keep the input looking like a short circuit. So its input impedance is basically 0, and it's an ideal ammeter in that sense. The practical implementation makes it slightly non-ideal, but you can make an extremely good feedback microammeter that is within certain bandwidth or within certain current ranges, almost perfect. A lot of that comes down to the choice of the op-amp that you use to implement the TIA. In this particular one that I've built today, I used a TL072, which is kind of old JFET input op-amp. It has very low input bias currents and input resistance. Its input resistance is about equivalent to about a gigohm. The input bias current is about 20 picoamperes at room temperature, and worst case it's about 20 nanoamp. If at full, I think is it rated 125 or 85? I'm not sure. But anyway, at high temperatures, the input bias currents go up. But it has pretty good performance. It's also a 2 meg part. Typically, they actually go a little bit faster than that, and has fairly low offset voltage. I mean, by no means this is a great op-amp, right? It was a good op-amp 30 years ago. There are much better devices available, but they're common, they're cheap, and for measuring, like down to about 100 nanoamperes, maybe a little bit lower, they're absolutely adequate. So you can use if you really wanted to try, you could use the TL 071 that has the offset nulling pot option. It's only a single op-amp, not a dual op-amp. I chose to use a dual op-amp so that I could implement the rail splitter for have a single power supply. You don't obviously need to do it that way, and you could use a more modern op-amp, but this is not meant to be a precision piece of equipment, just something that can measure fairly small currents for different purposes, and we'll show a practical example of that in a minute. How it works: you've got an op-amp here it's in feedback. This is the feedback resistor. The op-amp is comparing the input node voltage to this reference voltage. The output will swing such as to reduce this to almost 0, just have the offsets. So this resistor sets the transimpedance, and therefore the voltage that you will see based on the amount of current being sourced or sunk out of this node. It is fundamentally inverting, so if you source current into this node, it'll swing negative to sink that current, and the output voltage will be negative. But it's bipolar, so it works at AC, which is actually a really good feature. You need to compensate this because of capacitances here. The thing can oscillate or have gain peaking at higher frequencies. So the way I did it, basically you put a capacitor across here to kill some of its HF gain. The way I actually set that up was that I picked the highest transimpedance feedback resistor, which is a 10 meg resistor. I put that in there, and I put a trimmer across here, and I just kind of injected a square wave through a 10k resistor from my signal generator. Actually, that was it? No, it was more than that. It was a lot more than that. It was more like 1 meg, I think, and a fairly low voltage. But anyway, I wanted a nice square wave, and then I adjusted the capacitor until I got sharp edges and no ringing, and that was sufficient to basically compensate the other ranges as well, where the lower resistances will be less of a problem. I also added the option to connect a much larger capacitor, 100 nanofarads or 1 microfarad, across the feedback resistor to kill the HF response completely, and that's useful for time averaging currents that are very short in duration. I found that particularly useful for the object that I'm about to show you here that has very pulsatile current consumption. But for something like a photodiode amplifier, because remember this is essentially a transimpedance amplifier, you can put a photodiode or a solar cell here and make a light meter, or make a way of measuring photocurrents or leakage currents. I actually have a picoammeter on my website, which I made many years ago. This is essentially exactly the same circuit, except it's a little bit, in some ways, a little bit nicer, but it doesn't go down to picoamps. It used an op amp with a femto or 10 femtoampere input bias current. This device will not do that, but it's fine to go down to like 100 nanoamperes per volt. I set it up so that the most insensitive range will be basically 1 milliamp per volt. It rails out at about 2.7 volts, maybe, using a 7.2 volt power source. So I currently, practical circuit. I've got one of these rechargeable 2S 9 volt cells, or they're actually about 7.2 volts, and I'm powering off that. The rail splitter divides that. So this is the rail splitter here. It's your typical op amp. It's just got resistors that divide the power supply rails and buffer that, and that's then driving ground, what is effectively ground. So you consider that this whole thing sort of just floats. That can actually be a problem with your instrumentation. If you did what I did and I actually swapped the inputs around such that it's not in, or doesn't look like it's inverting, and you source current into the ground basically, then it will have a positive output voltage. So I labeled the inputs, as you can see here, red and red. So current into here means voltage out of here, voltage increases. If you do that though, that basically means that this and this are shorted together. So if your instrumentation that you're using, say your signal generator when you're calibrating it or compensating it, is such that the grounds are now will cause the op amp to rail basically. So what I did is, just when I was doing the compensation, I fed the signal generator ground into this side and the current limited voltage into this side. Anyway, minor detail. In operation, the thing's used floating with a multimeter. So, well, typically used floating with a multimeter, although right now I have it hooked up to my oscilloscope so that we can actually look at the time domain as well. But just something to bear in mind. Okay, so here I have a calculator. It's I actually think I damaged it a little bit opening it up, because the case doesn't really, lend itself to being open to replace the battery, which is unfortunate. Anyway, I sorted some wires to where the battery should be, bought them out. There's the original battery clamped between two test leads just to give me 1.5 volts. And I've put that in series. I put the current meter here in series with it. And if we turn it on, I've also put my little EMO probe here to listen to the electromagnetic noise from the calculator and give us an idea what's going on. So if I turn it on, let's make this a little easier to see. Okay, turn it on. You can hear that it's pulling pulses of current, and it's reading 220 millivolts at the moment output from the transimpedance amplifier. You can see the transimpedance amplifier is currently set to the middle of the gains, so that's 10 microamperes per volt. In other words, this is pulling about 2.2 microamps, which is not very much, really. It's surprisingly efficient. Now, interestingly, if I put more stuff on the display, it starts pulling a little bit more current with each segment that has to be driven. You can see I hear the sound changes a little bit too. And if I do something complicated like square root, it takes a pulse of current to do that. And that's not particularly interesting on the multimeter. You can just see that the average current went up a little bit. Obviously, if I clear the screen here, it pulls less current. Holding down a key pulls current about 2 microamps actually. Even the off button, interestingly enough, pulls about 2.5 microamps just if I hold the off button down. Now there's the display being screwed up because I damaged it when I took it apart, but there we go. Now, in the time domain, it looks like this. So, start with it off. And now I turn it on. There's a bit of an inrush current, and it's pulling about, 2-ish, 2.2 microamps. Then if I put some 8s on the display, you can see each button press pulls a clump of current. And then if I do a square root, each time I do a square root it has to think for a little while and it pulls some current doing it. Multiplication takes a lot less, for example. And addition, pretty short pulses for addition. Alrighty, back to off. So there we go, super simple circuit, extremely useful. You can obviously make one that's sensitive right down to picoamperes if you wanted to. If you do that, you want to shield the entire thing. So you want to build it inside like an Altoids tin or similar, have a nice connector, and make sure the circuit is super clean. Like everything has to be absolutely leak-free when you get down to those kind of currents, because even a fingerprint or an eyelash will make it rail out, basically, it'll leak current. But yeah, useful little device. I think it will be useful for some of our projects in the future, but it's also just a generally good adapter to have around the bench. Alrighty, see you tomorrow. Bye.